Okay, the experiment that will be part of this lecture is written up. This was a class project at the University of Southern California, otherwise known as the University of Spoiled Children. I don't know if you've read about them in the news, but there were these people who paid millions of dollars to get in to the university. But anyway, we had a bunch of pre-med students that really didn't want to be in any sort of science course. So I had just discovered the effect I'm going to show you today with a Super Ball, and it turned into a project that eventually ended up in the American Journal of Physics. And you're welcome to take a look at it. Now, none of the fancy stuff that we're doing with the velocity vectors and all that, I didn't know that then. So it's a dull equation, old way of doing in that particular paper, but it's was kind of revelatory at the time. And we got on the CBS News, NBC News. I mean, the popularity of this little Project Ball is what it was called, grew beyond what anything I thought would happen. I call it faux flubber. It flubbers, that rubber that bounces higher and higher, and this kind of acts that way, so that's a good name. Anyway, I want to show the mechanics of this somewhat dangerous device. I'll show you a picture, but also I want to point out that this link right here is two interesting things like this that are in the American Journal of Physics. Now, they publicize interesting things, just not real well, but once you get to this link, you can explore them. So if you have any extra time, lots of interesting things available. The interesting thing, of course, we're going to do today is look at the Super Ball version of this. This is just a review in the textbook that we went over rather rapidly last time. Anyway, I want to introduce this independent bounce model for collisions that solved the Super Ball problem. At the time I first did this, it was kind of by accident, and this idea of sticking a pin in a Super Ball and dropping it. This is the simulation here. It probably wouldn't hurt for us to go ahead and do the experiment. Now, it's not so dangerous in here because we have a rug instead of a solid floor, but I'll also try to do the experiment on a heavy piece of metal similar to what's imagined in this particular diagram here. In any case, this is an original Super Ball. This was invented by Whamo, and it was discovered by accident, just like this effect that I'm showing you was discovered by accident by me. What had happened was I had made tried to figure out a mechanics problem that involved grabbing a sphere that was rotating at a particular point and then trying to figure out what it would do. And at that time I was pretty clumsy with the mathematics. So I was having trouble. I thought an experiment would do it. I knew that the Super Ball, when it hit the thing, would rebound with the rotation as well as velocity. So I had stuck a pin into a Super Ball. It was not as long as that one, but I told you it was dangerous, but not that dangerous. See, the rug really takes a lot of energy out of this. To do a better experiment, I'll try to do it from this tower and land on that heavy thing there that does not rebound very much. Find a little hole here, and I will try to release it after it stops swinging. Stop swinging.
It hit her, yeah.
It was such a good shot that it hit that. Very often, it sticks it in the ceiling. That's how fast it goes, and if it just happens to rotate to there, that's where it is. That's what happened to me the first time I did the experiment trying to do the bounce. And I was really frustrated with the problem. But then when the pin disappeared, I mean, I didn't see it going. It was so fast, and I didn't hear it. And so I just started swearing, blank, blank, blank. And a friend next door in the office comes in, "What's the matter, Bill?" And I said, this problem is great. And he says, why do you have a pen stuck in the ceiling? And there was a pen stuck in the ceiling. So that's how I discovered his effect. I could have also put out my eye. I mean, that's, I point out to you that if you do experiments with a lot of kids in a laboratory, I guess you better get the plastic glasses out. In any case, that's really a good lesson in the kind of mechanics of collisions that we're trying to learn here. And now we're going to get very quantitative with it to see some other things that we didn't mention just for these car collisions here. This has some interesting applications, I think, as well. And later, our paper wasn't known that much by everyone, but it's an American Journal of Physics, and only a few physicists read that. Later, Sterling Colgate, the famous astrophysicist, that developed the first models for type 1a supernova, rediscovered the superball thing, and in fact made a product which I'll show it to you later on. We're going to play with it later on in the course. But the idea, if 2 can do this, 3 can do it better, and 4, and so on. And that was what Project Ball was really about, is trying to figure out how a train of balls could get something to really go fast. So that comes later in Chapter 8. Anyway, we've got enough to do just with 2. And also figuring out the basic idea of an independent bounce model. And at first, when I discovered this thing, I had no idea how to explain it. Here's our liability disclaimers. Should have, by law, tell you. In any case, the idea of this and the project that went with it is probably wouldn't have happened at all, except a couple of the dental school majors were really good at making things. Came in the day after I demonstrated by hand and said, and I was having trouble, you move it a little bit, it goes that way, you move it, it goes that way, right? It was really hard to get the thing to go straight up. And it was an auditorium, so it hit the ceiling in a large auditorium when you have a hard floor. And so it was spectacular enough that people in the class, at least these dental, pre-dental majors, brought in, and they had made this thing that had magnets at the end. I mean, it was amazing for me to see that, and it just struck me, my gosh, if these guys are that interested, we have to do something with this project. It led to Project Ball. But the idea was that you have a little thing that drops it and then gets out of the way. So what happened here doesn't happen. And the pin gets to fly as fast, as high as it can go. And then, of course, the whole idea of doing multiple balls came in very quickly. In any case, just to give you the sort of the algebraic notation that we use, and this is in the Chapter 3 of the first unit that we're working on right now, and the idea of labeling the various points starting here. So what we're going to do today, using the graph paper that's on your desk, this is a piece of it right there, is we're going to start off just going through the collision before they do the big jump. In other words, the 2 balls and the pen will be called a ball. That turned out to be really necessary in this project. If you just use the pen a couple of times, the ball disintegrated. And that's the other thing about the superball rubber, is that it's quite brittle at high velocities. Anyway, we have on a velocity graph, and I'm going to actually do 2 of them here, one of them on a larger scale, and then one on a smaller scale where we can go over the entire phase space of the collisions. Your paper is big enough to just do 1 graph. You've got enough real estate there that I don't need to make 2, you don't need to make 2 graphs. But let me just start off with where we are in a collision experiment. What we're going to be doing is starting at this point right here, where we have a -1 velocity v1. Now v1, that means the velocity of the heavier object here, in this case the SUV in our experiment yesterday. This is the super ball, and then the second one up here is that pen, but it would be another smaller super ball in the experiment that we did in the USC. The basic idea being that we wanted to get more than just two, but all that we're going to talk about today is two, and they start off right here with both of the velocities -1. We'll take that B as the unit of velocity, so we don't have to worry about units that much. Everything is defined by that initial thing. And the whole thing that solved this problem, I really didn't have any idea how this ball was giving all of that energy to that pen until I was forced to really think about it, to use it in the class in the first place, in that pre-dental class. And I just thought, well, my gosh, this is weird material. It must have a shock wave that goes through the ball and then spits out the pen. I mean, it's complete garbage, but it's all I had for the zeroth approximation to solving this problem. But then I kept thinking about it, and I thought finally, what if we could think of it as having the ball hit, bend a little bit, and then rebound before the pen really knows that anything's happened at all. In other words, make the two collisions, first with the floor, and then second between the ball and the pen, as independent. So that's why this is called the IBM, Independent Bounce Model. Okay, IBM being the company that missed out getting trillions of dollars by thinking that every computer had to be a monster. So the idea here is, let's take it one step at a time. That is, have the M1 turn around completely, and then we'll have a collision between the two. That is, well, it's like a freeway collision, except now with a ratio of 7-to-1. The pen's typically 10 grams. The ball, this particular ball that we have here is about 75, or some of them are 70 grams. So it's a 7-to-1 ratio that we're going to be dealing with here. A little bit higher than the ratio that we had in the SUV, which was 4-to-1. Okay, so we're going for 7-to-1 on this first part of the lecture today. So that's the basic idea. So I'm going to have the first collision take place as just a horizontal motion on the graph. So the first thing you should draw on your graph is a line or an arrow indicating that you have had a collision with the floor. So this is the ball hits floor collision that goes across here like that. So you put a little arrow on that to indicate the first move in this thing. And then you know what to do if you have the SUV hitting a stationary Volkswagen. This is the big ball hitting a stationary, or I should say in this case, with a head-on collision, a ball that's going, and this is the pen here, with a -1 velocity is going to hit the ball that's coming up with a +1 velocity. Okay? So that's the next step in this idea, in this cartoon right here. But let's go ahead. Now I'm going to skip this little bit of discussion about the collision of this thing with that plate. If this was 10 kilograms, we'd have to worry about the recoil of something that weighed 10 kilograms by something that weighed 70 grams That's what that diagram is trying to show. In this case, I have a long ellipse there that is representing that. And of course, this is attached to the Earth, so there would be a really long ellipse if I were going into that. In any case, that all collapses into this line as far as we're concerned with a precision for the thing that we're doing right here. So the next stop after this, this is, I guess we'd call it the Zero Spangler. We were calling it the first bang here. The basic idea is that right there. After the thing has gotten, the first mass, the M1, has gotten all of its speed turned around from minus velocity to plus velocity, then it's a collision like we did yesterday with the SUV hitting the VW, only now it's that big 70-gram mass hitting a 10-gram pen, so 7 to 1, much more spectacular. And so what you have to do then is put a line with a slope that's equal to the mass ratios. In this case, the light mass on the bottom and the heavy mass on the side here. So we're talking 7 to 1. So what you have to do on that piece of graph paper is find a convenient size square, and there are lots of them there, and just simply start counting. You count 1, that's minus 1 actually, and then you go 1, 2, 3, 4, 5, 6, and 7. Okay, and you put a dot. All right? So make sure I did that right. I've got little squares that you maybe can't see from where you're sitting, the dark squares I'm counting, but you've got a much clearer thing involving your graph paper. So let me check again here. I went 1 this way, and then I go, that's minus 1. Then I go plus 1, 2, 3, 4, 5, 6, 7. Then I do it again. I go minus 1, and then I climb up plus 1, 2, 3, 4, 5, 6, and 7. Okay? I put a big dot there. And then I make sure I've done that right, just like we did yesterday. Would help to do it again if you wanted to really make this thing precise. But that's probably good enough for folk music right there. So that is the line along which this system will travel in the very brief moment of collision after the first bounce, if you want to call that the zeroth bounce of the big ball off the thing. Now the two of them follow this line. And where it stops, well, that we have to figure out. But I think we've already learned the technology that's required to do that. Now what you already have on your graph is the line that helps you do that, the collision line, the COM line, or whatever you want to call it, depending on what you're doing here. There is a line going through this 45-degree line, and there would be the center of momentum point that you would stop at if this super glue was holding the ball and the pen to each other so it couldn't escape. This would be where you'd wind up. Okay, if you lost all the energy you could possibly lose, that would be the thing that would tell us. So that point right there is very important. And it's the one where we're going to put the compass down to make the circle that goes clear around to the solution that we want, somewhere up here. Yeah.
Where's the pink line for? Like the red one you say?
This one
Yeah.
is the same as what we did here. Okay? So it's the, you remember when I asked the question, where does it end in a crunch? Right, and you get a partial answer, and that's where the two have the same coordinate velocity, right? So wherever, somewhere on the line where they're equal. So that's the COM point right here. I'll just go ahead and write it. COM, center of momentum. And then it's a stretch for this compass to do this. I have actually a better compass, but it's harder to use on the board. So I'm put the chalk right at that point. Put this guy right there. And let's see where we wind up. I draw the circle all the way around. And I run into the ruler over here, but that's okay. Come out up here. Oh, I slipped a little bit. And, oh, I slipped a little bit more there, but let me get back. And there's where we wind up. Now, how close does that to the right answer? We're going to see that in a minute. Putting down here temporarily that point. I can see it's a tiny bit off, but that's pretty much where it is. It's 2.5, and it looks like it's a little more than 2.5. Increase in velocity, factor, okay, whatever the initial velocity is. So we're in these units, the units that the thing has when it hits the floor. Okay, that particular velocity is the velocity unit we're using here. Okay, so far so good. Okay. Now if, in fact, in the lecture hall, this experiment was perfect and it really did come off with that velocity, how much higher than where I dropped it does it go? Is it 7 times higher? That would be pretty spectacular, but is that right? Is that approximately right? Okay, now this is a question that as you get better at this stuff, it should just be obvious. You should just be able to snap to the answer to this one. Okay, now you've all had elementary physics, you sort of university, what we call university physics, right? And you would solve this problem fairly easily, right? Am I right or am I wrong? Okay. Anybody have a guess for, is it 7? How many people think it is 7 times? I drop it from 6 feet, goes to 42. Is that right? No, he shakes his head. So what? You're closer to right. What is the answer? Now remember that the energy, as far as potential energy and gravity, right? Constant gravity, right? That's linear with height, right? It's a good approximation, right? And we're talking about kinetic energy, right? So what do you do with that 7 to figure out how it goes?
Oh, square.
Yes. Now, as I said, it's these kind of questions that you should be really good at. This is something Feynman emphasized. You know, this is where you're really thinking critically. You've got it, you know, at the tip of your tongue or tip of your brain or whatever, something to get it out, okay? So the answer here, when I'm talking about getting 2.5 times velocity, I square 2.5, okay? Talking about 6 or so. Okay? That's the result on the coordinate graph that we will try to draw later on. But that's the basic idea of this. And what we have on this graph right here is much more to the point. This is 2.5 exactly. I've got just the graph on the blackboard that I made myself is not that accurate, but this is good. Okay, and that should be what you got on your paper. Okay, so it's 2.5 squared is the height that the thing goes. Okay, so I'm dropping it at 6 feet. I'm getting about I'm getting a spectacular height out of this. Okay, let's see if there's anything else that I should mention about this, and that is what we can do here is ask ourselves, what happens if we have a ceiling and it bounces back down. Of course, the ceiling's not uniform and all, that's not really perfect collision, but we can simulate a situation where that occurs, and that's what we'll do, just to make something that's really neat to look at and also think about. So there's our final point right there, and the ball will bounce up, the 70-gram ball will bounce up whatever height is associated with the square unit here of a half. So it'll go in distance units about a quarter, where this one's going 2.5 in terms of velocity, 2.5 squared, 6.25 basically is the factor that you'd have there. Okay, now once you have a graph like this, and this is the thing I really want to emphasize, is the advantage of geometry is it allows you to use the visual part of your head. And the visual part of your head is much faster than the logical part. As a graphics accelerator in a computer is faster than the main CPU. And the reason for that being fast is partly because they don't have to do all the qubit checks just to get a position of a pixel. So the same seems something like that seems to be true of your visual system that talks about how things are going to work. And having a visual thing like this is good because if I want to change the mass ratio, you don't have to go back and do a formula over with. I can just put the ruler down here through that point and change the slope to something else. Okay? So for example, if I just pick that, instead of having a 7-to-1 a slope, minus 7-to-1, I've got something that's roughly 3-to-1. Okay? So draw another line. All right? Go ahead and do it. I don't care what slope you take. Once you've drawn that line, it's going to intersect the COM in a different place, right? So at that juncture, you put your compass point down on that point and redo the circle. Okay, and obviously you will be getting a different result. A difference that gets quite a bit bigger as we go up. Oops, I slip again. It's hard to hold that thing there. That's part of the reason that last one. But in any case, I'm going to be hitting that guy. Ugh, keep slipping. Paper is so much easier because your compass sticks with this little needle on the point you're interested in. In any case, here's the new result for a slope of roughly 4-to-1 in mass ratio. Okay, so 4-to-1 is what we talked about with the SUV and the VW. So there's that experiment right there. Okay, let's try an even lighter pen. Instead of 7-to-1, let's do 10 or 15 or doesn't matter too much. I'll go ahead and I'll set this thing over in the middle somewhere, about there. So I can draw another collision velocity line. And I hit higher up on the COM line right there. And then I just keep on going. And I'd better go, you know, all the way to the top just to be safe. I don't know where on there exactly I'm going to hit, but the compass is going to tell me that. So here's another compass circle that we're going to be drawing. Only, only this one involves a slightly larger radius. And let me see if I can get this one right without slipping. So I make a really big circle here, and it goes around the corner here, misses the ruler, and then comes back, and I'm going to try really hard not to slip that point, and see where I lined up. Oh, it slipped a little bit there. Get back on track, and go, okay? And it looks like it'll hit about there, okay? I'll make a great big dot there because it's a little bit off. Okay, well anyway, what you're seeing here is 3 dots. They look like they're forming a pretty straight line. Is that right? Is this thing linear? Is this complicated stuff with all the circles and things coming out linear? Let's try again here with a slope of 3.5 or so to 1. I'm just picking it out here, and I'll go ahead and put that's velocity line down. Now, by the way, there's a geometrical name for this family of lines that I'm making here. It's called a pencil. And it's pretty obvious why they call it a pencil. When you take an old-fashioned pencil and sharpen it with a knife like they had to for hundreds of years, it looks like that. There's the point of the pencil right there, and there are the lines from the cutting of the pencil, right? So there's a pencil of lines, and there's lots of theorems about that pencil. But one of them you're about to rediscover here. You remember your geometry, you know that the proportionality of a pencil is always the same from the point measured. But let's get busy and we'll get the circle. And this will be a smaller circle. It comes off of our initial pen thing. I'm going to again try to be careful. See if I can keep my point on there. Come up here and hit that particular. And there it is. Okay? So we've got another point right there. Well, I can see something that's really simple here. They seem to be heading toward 2. If I go down a little bit in the slope here, okay, say I go right here, draw that guy. Let's make this pencil a little fatter. Just put it right through there. Go on there. Maybe the circle will hit higher, but in fact will not. That is the answer for a slope of 3 to 1. It takes all of the energy and velocity out of the ball and puts it in the pen. This is 100% transferal. Isn't that cool? Let's see if it really works with our construction. Okay? I'm going to be drawing the smallest circle that we've drawn so far. Goes right through there and goes right through there. Okay? Now, given that the distance to the red line from the point ratioed with the distance from that line to our interesting points is always the same. I mean, it's a circle, right? Has the same radius here as it did here in every case. That has to be a 45-degree line of all possible solutions for different mass ratios. Pretty neat, huh? And that includes a ratio of approaching infinity right here. If I take the super ball and put a little speck of dust on it, and I don't have to worry about all residual Coulomb effects and things like that, I drop that thing and the piece of dust comes up with 9 times the height, 3 times the velocity from this point. 3. Okay. Here it only comes up with 2, so it goes 4 times as high. But this one, if I could see it, and it's a good thing this doesn't happen because every time I drop the super ball, I'd probably blind myself, right? Well, it's on some little piece of sand, right, that was on the top of the super ball. Okay? All right. Now, we can continue on to the heavier and heavier pens, and as we do that, you're simply going to be following a line here, but now you know something has to happen. The pen has been driven back, the super ball has been driven back into the floor. It's going to rebound. So you can draw a line like we are doing here, but it's going to come out here when it bounces back, right? We'll talk about that later on. But this is, I think, already an interesting example of how fiddling around with geometry can get you a lot of interesting stuff. So I'm just going to draw a dashed line, or first I'll draw a solid line through these guys, and then these are other possible, excuse me, I should have drawn it down there a little bit. Anyway, that is the end point for all the possible collisions as far as the pen is concerned. In this model, this is the independent balance model that we're taking here. And like all models, it's not perfect. We'll discuss later on why it exists and is accurate, but also nothing. But this is interesting right here, because what this says is that we have 100% transfer. The ball is going to give it all. And we have an example of that that's pretty close. And this just shouldn't work, but it does pretty well. I'm going to grab this ball right here, which is a 60 grammer. And this is a pen that doesn't write very well. It's just a brass rod machined on the lathe, and I kept taking stuff off until I had a 20 gram pen. So this is a 3-to-1 situation right here. And I've got a hole marked here that I'm going to stick the pen in, and then I'm just going to drop it in the corner right here. And except for a little bouncing, it just rolls away, and the pen comes flying out, this time presumably close to twice the velocity. But it obviously wasn't that. It didn't. I dropped it from here, and it didn't make it to 4, which is here, but it got about here, right? So it's pretty close. So there's an example of this particular system giving it all. All the energy has been put into the top, the thing that's flying. Okay, does this make sense? And also, does it show you the power of using geometry to display results? Make a sketch of something that's going on and make it quantitative as well. Okay, well, today I'm kind of using both of these. I think they're clear enough that I don't need to go to the all auxiliaries screens. But let's just go ahead here and point out what it is we just did. This line here, elastic collision final point locus, that's the fancy name mathematicians would give to the solutions. It's just parallel to the center of momentum line. So we went from 4 to 1, 7 to 1, 15 to 1. Infinity is right there. The most velocity gain I can get from this gadget, according to this theory, is an increase in velocity of 3.0. Well, that's when we said, hey, yeah, but that's just with 2. With 3, whoa, we can really talk business. And with 4, we didn't get very many experiments of that, because either the ball disintegrated, or in the cases that we tried it outside, we lost the last ball. I mean, it's like a gun. It just shoots the things madly into the sky. So that is, I think, a pretty good lesson for just getting a visualization and making something interesting happen. Okay, let's see if there's anything else I need to say about that 15 to 1, for example, gets you right here. So infinity to 1. Wow, that little piece of sand, according to this, would really fly. We're lucky. There's lots of residual Coulomb, van der Waals, you name it, forces that keep things that are small from coming off of the superball. Be thankful, because I probably would have blinded myself with this. Now, what I'd like to do, just fairly quickly here, and this will become a problem later on. As you already know, I didn't realize Labor Day was Monday the 2nd when I had signed the homework for it, so Wednesday is when it's due now. But after that homework will be something that involves this. So I want to get started on that. But also just answer the question, can we use geometry to finish this? Now we're just calculating the velocities that happen, but can we get the positions? And if we can, what does that mean? Can we get the time behavior of this if we allow it to live in a box where it bounces back and forth? That's the next thing I want to consider. And that's something that you can do on an air track. Air tracks really, I think, were revelatory, that is revealing to people that were taking mechanics that something that doesn't have friction on it maintains its momentum, its velocity. So on a air track, you push something, it just goes very nicely, keeps the speed, bong, and comes back very nicely, okay? But after a while it wears out because there is air resistance. Now we have superconductor. You can make superconducting cars and they have very little friction. They literally will be still going when you go home at night and come back in the morning, if you can keep the superconductors working. This is the room temperature, nearly room temperature, well, it's liquid nitrogen temperature superconductors, which were first done here. So that's when we got to actually play with something like that. But in any case, what I want to do is go ahead and explore some of those results. But now I just want to get this much done here. The basic idea that I'm wrestling with here is if I have to find position, that is, after I've done all of this work to get the velocity of some collision that has yielded the two objects, the ball and the pin, let's say, with some point, some velocity for one and some velocity for the other, and just back up here and say that this means that M2 is somewhere on some path of slope, and this gives the slope, okay? So what we're talking about here is integrating the results that we have here. We have velocities which are derivatives of the position and we'd like to get the position. So this is a lesson in geometrical integration, and it's a heck of a lot simpler than the kind of integration you have to do with calculus, because everything is at constant velocity. So we've got all of the possible answers as being lines with the slope that we have found by this geometry over here. So by this geometry has given me a minus 0.5 for the upper object, and it has given me for the lower object, the ball, the driver, 1.0. So the answer for where they are in space, this is space right here, okay, height, and we've got two objects here, so we've got to do this twice. First is the red guy, the hot one that's got the velocity, could have the really high velocities in our experiment. There's a line of slope, minus 0.5 over here, somewhere, okay? And then this one's telling me that the velocity is 1.0 for the other object. Well, that object has a slope of 1.0, but it's, where is it, you see? So you have to, at this point, say, okay, I've got to know some initial condition. I've got to know at a certain time, say time equals 0, that it was in a particular place. Say there for the hot one, and there for the cool one, say right there. Okay. And then I'll just draw a line with that slope that I figured out over here. Okay? So there's a really crazy integration procedure. It's not crazy, it's very geometrical. It's something that Thales could have done in 600 BCE. Okay? So that's what we're going to do. It's sort of spelled out right here, and I'll put it on this screen as well. What we are going to do is assume that the pen was at 3 units at time equals 0, and the ball was at 1 unit, and they were falling. That was our initial situation when we were over here. Okay, so at this particular moment, the two objects showed up very close to the floor with -1 velocity, both of them. So that just means that wherever they were, and you can imagine the ball's here and the pen's here, at 3 and 1. So that's just a given. I'm just taking that as a given. And then we draw lines with slope -1, because that's the speed that we are. Then the geometrical units of velocity are being shown as slopes with a particular geometrical time choice. We're not being very careful getting MKS here, we're getting whatever's convenient. And then proceeding to draw these lines until something happens. And the thing that happened first over there was the independent collision of the ball with the floor. And that is pretty easy to figure out. Assuming that it's elastic, as we are assuming everywhere here, the thing is going to bounce with exactly the slope of the sign changed that it had coming in. So now it's going to have slope 1. And at some point it's going to run into the thing coming down. And that's where we're going to get our space versus time thing. And that's what mechanics is all about. Different ways to catalog what's going on to a mechanical system. This is telling you where things are at a given time. The other thing that we need to know is a little bit more complicated, but pretty simple, almost as simple as that. But let's just go ahead and finish this. This I'm going to go ahead and do on the graph over here, and you should do it too, because you'll be starting up, I'll be giving a problem that carries this through to pretty good finish. So here's guy pen starting out at time equals 0, and here's the ball right here starting out at time equals 0, okay? This guy's at 3 units height, and this guy's at 1 unit. And they're both going with velocity minus 1. So that means a slope here of minus 1, literally, in a space-time graph. Now if this guy, this pen here, is never going to run into anything, it would just keep going, down this line here at minus 45 degrees, and eventually hit the floor here. But there's this guy here also doing that. This is the ball, which I'll draw with a little thicker line, coming down to the floor. I'll make that line extra thick, because he's big and fat. Okay, hits the floor right there, and assuming elastically bounces back, and runs into the pen coming down right at the altitude of 1. Okay, so we made this fairly simple. Get a long piece of chalk here, and draw the ball coming up. Okay, make that fat, that line. Okay, and the pen coming down and running into each other. So this is the collision, which will leave with certain velocity depending on the mass ratio, and that's what we were just figuring out with this kind of geometry right here. So that is the idea of how you let the geometry be carried through to the integrals of the velocity here. So this is a space versus time graph. This is a Newtonian graph. We have the space here and the time here. We already have mentioned that there are reasons why Minkowski, Einstein's math teacher, but finally Einstein and everybody else that does relativity, does it in such a way that the time, that's this guy. Now let me see if I just realized I'm using the wrong graph here. This is the one I should be using, so let me get up and onto that one. Sorry. This is the place where they
change your label.
This is, because we do need this graph for, we're going to do that with a different thing. This is configuration space, this is space-time. And there's the ball's trajectory right there. Your graph is carefully marked with the coordinates in coordinate versus time. So you probably didn't make the same mistake I did at this point. But then coming down here and running into the ball is the pin. Okay, so there we go. Okay, so collision. Now you have to know what velocities we got from the collision, assuming the collision is independent. These motions are independent. It's just two things running into each other in space at that moment. So the next step on this thing is to use that thing. Now, the question, of course, is what is the answer to that? And that's where you have to look at what we just did here and producing a 7-to-1 collision winding up here with a velocity of 2.5. So we're going to have to be drawing a line with a slope of 2.5 right there. I'll go ahead and advance these two here to that point. Okay. So, and when we get done with having something go at 2.5, we're also going to be having, as we did have with this particular case right here, we're going to be having the lower mass, the one that's not going to be going so fast, this 2.5, sort of making the dot here bigger. Remember when I came through the first time, I got a little high there. But in any case, the answer is right in the center of that black square. 0.5 is the velocity measured by this coordinate right here, and 2.5 is the velocity measured from here, 1, 2.5. So those are the final coordinates, and we just simply have to draw lines with those slopes from that point. First, this one with a slope of 0.5, 1/2, there, and then this one with a slope of 2.5, which hits the ceiling, and then you have to know where the ceiling is, and that's what we're going to be doing in the next few days, is working out collisions that involve a whole bunch of balls running into each other inside a container, an air track or a superconducting track. Okay, so that's the order of the next few days, but we're going to take it a little bit further right here. Because the other thing we'd like to see is what does it look like in velocity space? That's what, I'm sorry, in space. What does it actually look like there? This is velocity, there's space, and then there's space-time. So those are the three things that classical mechanics works with. Three ways to represent what's happening in any situation. We've only got two things here, each with one dimension, 1 degree of freedom. So you can imagine that it gets really complicated when you have already 2 degrees of freedom for each of them. That's 4-dimensional space. And that's hard to visualize, really hard. We're getting better at it using computers. But 5 dimensions, 6 dimensions, and so forth, okay? There's a lot to do yet. There's a lot to do to play games like this that are geometrical with complicated mechanics. Any case, this is a situation that we just saw a little bit of the beginning of. The idea that after we've had one, this comes back down off of the ceiling, that's pretty easy. You just turn the slopes from plus to minus. So positive slope, whatever that was, 2.5, this is going to be minus 2.5. And this guy right here, he takes off, and they run into each other at that point, and then you have to do another one of these right here. That is, we did the thing that brought us up to this point right here. That was the first thing drawn right through there. Okay, so there's 0.5, 2.5, 2 is right here, 2.5 right there. Okay, then that bounces off the ceiling. Okay, and that's why I had to make a bigger graph over there to show that. That's the next stop after this occurs. And the velocity plots that we need to draw are going to be determined by this value. And then, and here's the problem, if that's the velocity space that this thing is in, I've got to go all the way from here to, well, I'm off the board, you see. So I had to do a smaller one over there. So what I would have you do now is just reproduce the part that we're interested in over here. We'll draw an arrow like we did here that indicates the first collision that involves only the ball and the floor. So we'll assume that's perfect. It completes right there. It has a certain velocity that's just the negative of the negative. That's a positive 1 velocity right there. And then we do on this graph the same thing. You don't have to do this because you already have a graph that goes out 1 and then up 1, 2, 3, 4, 5, 6, 7, and then does it again, 1, 2, 3, 4, 5, 6, 7,
Did I get that right? One, 2, 3, 4, 5, 6, 7, right? And I do it again here. 1, 2, 3, 4, 5, 6, 7. So there is the next velocity on this reduced scale graph, but it makes a graph that can cover the entire realm that these two objects are going to be able to go. Just get this thing to draw a nice line through there. Okay, so this is another velocity right here. And then it's going to hit, see if I've got that right. Yeah, so there is the coordinate 0.5 velocity for the heavy object, the pen, the ball. And then here is 2.5. That's 2.5 right there. Okay? Now, that 2.5 has to come out to minus 2.5 after it hits the ceiling. So this is a case where these objects are confined on both the top and the bottom by a ceiling and a floor. So the next stop here is way down here. I don't need to be very careful about this because we know the answer is right here. So this is going to be an arrow that comes all the way down to there. Still has a abscissa coordinate, horizontal coordinate of 0.5, but this is minus 0.5. Okay, so following the path, this collision path is across here, up to there, down to there. Okay? Now each of those stopping points, collision points or end points of collisions, okay, have velocities associated with them. Velocity vectors, and we use a slightly different colored chalk here to indicate them. Sort of a blue here to draw this one. There's an arrow going right here that's very important. This is a velocity vector in the particle space, the 1-2 space. Ball, pen, SUV, VW, whatever. So there's one vector that's of interest. And of course the vector that we had before this happened, I'll draw a slightly different color here, sort of a green. This is the setup for the actual collision between the two. It throws the little one so high, okay? And then, when we're done, here there's another blue vector right here. Okay, so these are all things that you should add to your graph in order to make use of what's coming. And that is simply a way to track in this space, this space right here, where things are. And this is quite spectacular when you get to use the computer to do that. But it's quite interesting. So I want to go ahead. We've got about 15 minutes left here in which I can discuss that. Before I do, though, let me remind you, for the problem that you're doing this due on the next Wednesday, getting the major and minor, actually, this is the minor and that's the major in this case, getting those radii of the ellipse, that is a key part of this, because once you've drawn the ellipse, and that's the thing that you should probably be noticing as we're drawing these graphs right here, is that all of these endpoints, this is the most recent one, the one before that we worked on so hard over here, and the one that we have right here, that is just a result of the ball bouncing, these all lie on the kinetic energy ellipse. So if any of your points are off of that ellipse that's already drawn, there's an error. Okay? So you see, if you draw the ellipse, if you have a way to draw the ellipse, then it makes the geometry a lot easier because you just bounce around until there are lines hitting the ellipse. Now, one of the things that I want to try to get to today is getting rid of the ellipse, getting the ellipse to be a circle. And that's something that's really unconventional, to say the least. And I'll let you be talking about that. In any case, I pointed out that when you have these collisions going on, and here's a good example of one, I'm going to go ahead and run it on this machine here, see if I can get that, got a mouse here, I'm going to see if I can get that started. This isn't going to be a Newtonian time plot, this is just going to be the thing. Let's just see how it works out. Yeah, there we go. Bang over, bang up, that's how far we got. Okay? And the way this program works is that it stops to let you see the high point of this second collision. And so what you want to do to get it going again is hit resume, and that's the part that we're talking about now. And you can pause this thing at any place, but you can see that I've just had another collision that went all the way over to that point on the ellipse. So that's what we're getting, that's what we're trying to find a decent way to get all of this structure. Now, to give you a little bit of historical context for this, that Feynman told me about, and then later it was published, and anybody who does statistical mechanics has learned this terrible lesson. When the Manhattan Project wound up, they had already a pretty good computer with anything like these things, but it, you know, was something like it could hold, you know, it had a memory somewhere around so many K, I think like 128K or something like that. But it was enough to solve differential equations reasonably well. And so they started taking famous problems like Fermi's mirror. There was something where you had a mirror that was just oscillating a sign and you had something that bounced back and forth. What they wanted to do was show that the fundamental axiom of statistical mechanics was that everything becomes completely random very quickly was true. Turns out it's not true at all. And they started noticing that. They figured there's something wrong with the computer. It was making all these patterns that were anything but random. And you're going to see that with this as you play with it. You're going to see situations where it doesn't do this. That's called ergodic, I call it ergodic filling. All these lines here, in certain situations, do pretty well fill this fairly quickly. But most of the time, it doesn't. It makes some kind of pattern. And that just blew their minds. You know, and that should have been the beginning of the chaos theory, but it wasn't. They just kind of dropped it until about 1980s when some people revisited that, and then we had a whole area where classical mechanics had to deal with what we call chaotic systems and the patterns that it makes. So we'll be able to do a little bit of that later on. In any case, this is a really simple way to have that available. So anytime you want, you just let this thing run. And what's fairly obvious with most of the ratios that you pick, this is 7 to 1. Is there anything special about 7 to 1? Yes, there is. Just about every number has something special about it when you start talking about what's going on in collisions of this complexity. So finally we end up with quite a few lines in there, but after a while it starts repeating. It starts going over the same lines. And that's it makes a pattern that occurs. And the question is, well, why does it do that? What, this really bugged me as much as it bugged guys like Fermi and Oolong Pasta and all those guys that were playing with this first computer back in I think 48 and 49 when they started playing with these things. In any case, when you do all of this, you also get patterns in these other spaces, in space-time and in space-space. This is particularly interesting because it's really hard to make a quantum mechanical problem out of bouncing particles, but particles are waves, and so this little thing here that always stays on this side, at least in the first go-around of these simulations that we're doing, it always stays on this side. This collision line comes together and they separate. They don't go through each other, but you can make them go through each other if you have a computer, and that's what we have, so you're going to be seeing some of that. In any case, the pictures that we're going to be looking at fairly shortly here involve, in this case I'm talking about a mass ratio of 7 squared. That's 49. I've got a 49 to 1 ratio. So what I get is a 7 to 1 ratio of ellipse, major to minor axis for that. And this is, first of all, quite beautiful just from its basic behavior at the beginnings of the motion. See if I can, what I want to get to is coming here fairly quickly, but there I see the click right here. It's due 49 to 1. First of all, Newtonian time plot. Let's see if I can get that to work. Oop, I didn't, because I didn't get the little hand to show. This is a little tricky here. I have to get on that, not that one, but that one.
I think that is the first one. It's just for some reason much better.
Maybe you're right. Let me just go ahead and see what we get here. Oh, okay, we get both. Yeah, that's fine. Okay, so this is the behavior that we're very familiar with. But now our line slope 49 to 1 is practically straight up and down. And it's that kind of picture that was sketched in the beginning of these lectures that we haven't really talked about, but when you have a big ratio, then this guy here has to be hit many times before he turns around. And then he does. Take that. And then he comes back. And now they're very close to this line, this 45-degree line, very close velocities. And then it does it all over again. So it's the pattern that lives in that squunchy little ellipse. It's pretty complicated. That's what we're going to spend some time with in the, next Wednesday when we have the next class after this. But here's something else I want you to see, and I'm going to pause this right here, and point out that there's a whole control panel for all of these things, and there's also all sorts of scenarios that you can play with, all the various things that we're going to be showing at different times during the course that involve collisions of multiple numbers of particles are all available here for you to mess with. But the thing that I want to show right here, instead of plotting velocity versus velocity, I want to do this plot that we started to make here, which is space versus space, the configuration space, coordinate space, where you would put a wave function if this was the quantum mechanical problem. Okay, so let's go ahead and start that with everything the same. And now what I would like to do in order to finish this is increase the scale. So I'm going to pause here. I'm going to go back to the controls, and I'm going to get my scale for the time constant, and help me a little bit here, TC, I seem to have forgotten where that would be.
Lower. It's right at the bottom of the page. You might need to scroll. T-max.
There,
One line down to your right.
down
No,
here.
now you got to go up.
Oh, okay.
Right under the word, right under plot range. To your right.
To the right.
T-max
Oh, here we go. Okay, let's take it from just 6 of our
disappears.
unit seconds to 4 or 5 times that. Let's try this. That ought to be good enough. Okay. Go ahead and start it. Okay. So now, big time for this to be carried out. Okay, bang. Bang. And it's picking up speed. And finally gets it turned around. And says one last clunk. And now they go up about the same speed, not quite the same, but pretty close. And this whole thing begins over again, except it's now a little higher. Whoa! It's really getting pounded by that. Now later on in chapter 6 of our unit, this is where we first introduced the idea of a force and a potential. Only the potential is created by very fast motion of something that's very light. In other words, this is a one-dimensional thermodynamics of a gas with one atom that causes pressure on the object that's impinging on that atom. Okay, we're going to use that as our model, as the simplest possible model of a gas. Boyle's law, all that kind of stuff comes out of mechanics, and you get it in a very beautiful way. So that, and now it's just about time to finish here. I do want to show a couple of things here. I'm going to escape and go back to the lectures and find a couple of things that I thought maybe I would have time to show here, but maybe I'm not. So we are going a little bit slower than we have in the past, and I think that's good. Perhaps in just the last few minutes here,
Yeah, space
if there are any questions. Yes,
Can you run the space plot?
that I would be glad to do, yeah. Let's go ahead and try that. To do that,
If you still got your browser up, we can do it in the control panel.
we can do it just right here. Just take this one.
Well, it should be still loaded in your browser. That'll work.
Oh,
Okay, now let's just straight away change it.
Let's
Controls.
pause right here and do what you're talking
That
about.
one up. That one right there.
There.
Plot the Y's. One down.
This way.
Yeah.
Okay, coordinates versus coordinate. Yes.
Yes, it's too close to. I can
It's,
see it better than him right here.
Let's go ahead and see what it does. Yeah, this is this space that we're drawing. Started to draw the wrong thing, the thing that's at the bottom there. So this is what you're getting in the space versus space, what you have to deal with there. So let's resume.
This is spectacular with this ratio.
Caught in the corner there, so to speak. Then comes out not quite along the line it went in on. Now the way Fermi, Pasta, and Ulam did their computer things was the balls didn't have any size; they were all particles, and that one, the scaling needs to be a little bit adjusted there. It does a whole bunch of stuff up in the corner there, and it comes out. You can do that on this thing by just simply reducing the radius of the balls to make them particles, so they actually come up to the line here, instead of having a gap that's the sum of the radii of these two objects. And then you get some of the behavior that two atoms in a linear box do as the time goes on. And the patterns are quite amazing that are made just by that simple system. So we'll be looking at that sort of behavior. But the other thing that we still have to do is a new way to handle the kinetic energy. The kinetic energy right now is a function of velocity. That's called a Lagrangian. Whenever any energy function has independent variables of velocity, it's a Lagrangian. The Hamiltonian, that's sort of the opposite. Their momentum is the independent variables. Halfway between there, something I call the Lagrangian. It doesn't have a name. I could be a conceited guy and name it the Harterian or something, but I'm not going to do that. I call it the Lagrangian, the stranger. And it's a circle instead of ellipse. The ellipse that we're dealing with now is a long one this way, the Hamiltonian is a long one this way, in between there is circle, and the circle makes the geometry really trivial. So you can follow these kind of crazy motions very much more easily. So that's the thing we'll be talking about very beginning on Wednesday. And I wish you a good Labor Day weekend. Stay cool.